Good morning, class. Today we are going to start the solar electrical panels. Okay, and the first thing that you as instructor should do is put your first name, last name, contact information, today's date, the module name, the unit, the lab, and the objectives. Today, the student will learn how to determine the gauge of the grounding conductor. Also, you have to have ready the material. So in this case, we are going to use the grounding conductor. Okay, this is number 6, the tools. So we have to have a set of tools, okay, on the proper bag, tool bag. So we need the tools. You have to distribute the tools at the very beginning of the lab. And each tool has to have the lineman, the dies, the long nose, wire strippers, a set of screwdrivers, Phillips and flat, okay, measurement tape, knife, and also in this case we are going to need this tool, okay, the BX, okay, the BX to we need this tool to work on the grounding conductor, okay, the armor grounding conductor, and the mirror. Part of the material, I need the clamp, the grounding, the bushing, the grounding bushing, and the copper rod. Okay, the copper rod. So before I start showing you how to calculate the gauge of the grounding conductor, I want to give you a brief introduction to the electrical circuit. Okay, an electrical circuit, single phase, include the following components: the source, the hot line that applies the power, the protection could be fuse, a circuit breaker, or a combination of both, the load, the neutral, which is the return of the electrical current, and the ground. When we apply the power, and if we zoom in a piece of copper, what we are doing is releasing electrons. In each atom, we have electrons and protons. The electron has negative electrical charge. The proton has positive electrical charge. Because of this, they attract each other. So in order to do an electrical job, we need to apply an external force. This external force is known as a voltage. The voltage breaks down this attraction, and then we have electrons in motion. The electron in motion is what we know as electrical current. And they are in charge to do the electrical job. When we release electrons, the electrons need to get back to the source using the neutral. If for any reason the neutral is broken or open in the middle of the way, so what we are going to have is an open circuit, and the electrons they will not be able to get back to the source. So they will stay around the load. If it is in the case of any appliance in a kitchen, a dwelling unit, the user could be electrocuted because the electrical current electrons stay there. And keep in mind, 0.5 ampere could stop your heart, human being heart. Okay, so we need to offer to my circuit an alternative way. We need to offer to the electrons an alternative way to get back to the source, which is my ground. My ground is the alternative way that the electrical current or electrons will use in case of the open on the neutral. And on that way, the ground will be used to close the circuit, not to continue working and continue providing power to the load. No, the ground is used to get back to the source and stop the electrical circuit. That is the reason we have to have a device that will detect imbalance between the neutral and the ground and trip the device, the circuit breaker, okay? The circuit breaker, ground protection, okay? And that is the reason why the NEC is requiring that we have GFCI or AFCI on the outlets, or the circuit breaker combo that include both protection, ground fault circuit interrupt or arc fault circuit interrupt when we have this kind of problem, okay? So we are going to use a dwelling unit as example. So my dwelling unit has 1,350 square feet. So we are going to start working with this as example to determine the gauge on my grounding conductor, and then I show you on the service panel. This is a service panel. Okay. As I told you, a service panel is an electrical panel at which the service company delivers the power, and it's the only place in a dwelling unit in which we have to have a grounding system, a ground. So we are going to use this service panel as example, and the dwelling unit that we are going to use is 1,350 square feet. Okay, right here, what we have is, as I told you, a dwelling unit whose total square footage is 1,350. Okay, that is my, and according the NEC table 220.12, I need to multiply the total square feet times 3 volt ampere. And in this case, I am getting 4,050 volt ampere. Also, the NEC on the article 220.52 parenthesis A is asking me to have available 2 branch circuits for small appliances in the kitchen. Each branch circuit should be 1,500 volt ampere times 2. I am getting a total of 3,000 volt ampere. And the NEC on the article 220.52 parenthesis B is asking me to reserve 1,500 volt ampere branch circuit for the laundry. And all of these together are known as a general lighting load. The general lighting load. So when I add all of this, I have a total of 8,550. Okay. the Article 220.42 is asking me, from this total, the first 3,000, you will be asking the service company for the 100%, which is 3,000 volt ampere. The rest, you will be requesting or asking for the 35%, okay? So if I subtract from 8,550 to 3,000, I get a total of 5,550. The first 3,000, I will be asking to the service company for the 3,000 volt ampere. For the rest, 35%, which is 1,943. If I add these two, I have a total of 4,943 volt ampere. This is what I need to be asking the service company for the general lighting load. For fixed appliances load, I have two options. I can use the information on the nameplate or use the table 420.248 for single-phase electrical motors, or 420.250 for three-phase electrical motor, and I use the horsepower to find out what is the full load capacity. Okay. In this case, these are single-phase electrical motor, so the hot water tank, I am using the nameplate. The nameplate in my hypothetical example is telling me that the hot water tank is demanding 4.5 kilovolt ampere at 240 volts. The total is 4,500 volt ampere. The dishwasher, 1.5 kilovolt, which is 1,500 volt ampere. And the disposal, garbage disposal, is an electrical motor, has half horsepower electrical motor working with 120 volt AC. According to this table, the 420.248, the full load capacity is 9.8 amps. If I multiply 120 volts times 9.8, I get a total of 1,176 volt ampere. For the blower, which is the motor at the top of the stove, is a 1/3 horsepower, working with 120 volts. And according to this table, 432.48, the full load capacity is 7.2 amperes. 120 times 7.2 amperes, I get a total of 8,864 volt ampere. If I add all of this, I get a total for the fixed appliances load of 8,040 volt ampere. If, according to Article 220.53, if I have 3 appliances in this section or less, I demand or I request from the service company for the 100%. If I have 4 or more, the 75%. I have 4 in my example, so I will be asking the service company to provide me for this dwelling unit with the 75% of this, which is 6,020 volt ampere. And on the other load, per section Article 220.14, I have the electrical range, the electrical dryer, the electrical heat, the air conditioning, and I should include the largest motor, which is my largest electrical motor, is this one. This is my largest electrical motor. So, and I have here, I use the nameplate information, the electrical range, 8,000 volt ampere in this hypothetical scenario, and the electrical dryer, 5,500 volt ampere. And the largest motor, per the Article 430.24, I need to multiply the volt ampere times 0.25, in other words, the 25%, for a total of 294 volt ampere. If I add all of this, I need to add the general lighting load, the fixed appliances load, plus these three, for a total of 24,767 volt ampere. How do I use this? I divide it by 240 volts because I have one or two devices working with 240 volts. And if I do that, I will have 24,764 volt ampere divided by 240 volts for a total of 103 amps. So, according to the table 310.16, okay, if I use that table, and the column, if nothing is said, I should use the column at 75 degrees Celsius, 167 degrees Fahrenheit, and that table is telling me that the gauge of the electrical conductor providing the power for this service panel should be gauge number 2. Okay, gauge number 2. That is the gauge number 2. So, how do I use this gauge? I need to use the table 250.66, 250.66. 250.66 250.66 to determine the grounding conductor, the grounding electrode gauge, which is number 8. For if the service conductor are 2 or smaller, the grounding electrode should be gauge number 8. If I use the other table, $250 106. Let's see. 250. $250, 102, parenthesis C, parenthesis 1. So if the ungrounded conductors are 2 or smaller, the grounding conductor side should be number 8 if I use copper, number 6 if I use aluminum. Okay, so that is the reason I brought number 6. Okay, keep in mind, NEC is asking me to do electrical installation at the minimum safety level. So the NEC for this scenario is asking me to use gauge number 8, but if I install and use gauge number 6, and the grounding conductor will be okay, because my safety level is higher.